This meeting is being recorded.
In this video, we're going to look at what are called cell diagrams, and we're going to also solve sample exercise 5 together. So what is a cell diagram? Well, it is a shorthand notation that we can use to indicate where our cathode and our anode reactions are. So for example, we have this cell diagram showed here. We always list the anode on the left-hand side. So this is going to be the anode information down here, or the reaction that's happening at the anode. And then down here, we'll see the reaction that's happening at the cathode. So the way that this is designated here, we have our solid phase electrode, our zinc electrode over here at the anode. Then we have this single line that separates our phases. So that's what we see over here. A single line separates the different phases of matter. So that's what we see with that single line there. Then we have this double line in the middle here. That indicates our salt bridge. So if you remember, the salt bridge kind of bridges our anode and our cathode voltaic cells together. So again, this is that salt bridge, and it's indicated with a double line. Then on the other side, we have our cathode information. So there we would see our reduction happening. So our copper that's in aqueous solution in our beaker here, that will be depositing on our copper electrode. So we have our solid phase electrode. Again, we separate with a single line showing our electrolyte solution and then our solid electrode. Sometimes there are electrodes that can be used that are referred to as inert electrodes here. And this implies that the electrode itself is not part of the reaction. So it's just establishing an electrical potential if we do not have a solid involved. So we'll see that in sample exercise 5 here, that our species that is being oxidized, the iron, is aqueous. So we're going to see that we need a solid site. In this case, the inert electrode here is a platinum electrode. And we also see that on the cathode side here as well. So we know that this is our anode, so we expect an oxidation half reaction. This is our cathode, so we would expect a reduction half reaction. So let's see what they ask us to do here. They just ask us to describe the half reaction and then the overall reaction that will occur in the voltaic cell represented by this cell diagram that we see here. All right, so first let's start by writing our oxidation reaction. So we know that iron must be oxidized, so it's going to go from Fe2 plus to Fe3 plus, and it will lose 1 electron in that process. Then over here, we'll write our reduction reaction. So we have our Cl2. We're going to reduce that. We're going to add 2 electrons to that to produce fluoride ions. And we know that we don't just have 1 here because we start with Cl2. So we have to include a coefficient of 2 here. So similarly to what we saw when we had to balance everything besides oxygen and hydrogen, when you had to balance those initial elements, other than that, we need to make sure that our chloride, both chlorines are accounted for with the 2 in front of the chloride. So now we have our 2 half reactions. Another step that we have to make sure of is that both of them have the same amount of electrons going in as going out. So here we see only 1 electron, so I'm going to multiply this equation by 2, and then I'll have temporarily now 2 Fe2 plus gives me 2 Fe3 plus 2 electrons. Over here I have 2 Cl2 plus 2 electrons gives me my 2 Cl negative. So now that I have everything balanced, the atoms, the charge, the electrons are balanced, now I can combine these 2 half reactions. So my overall reaction will be 2 Fe2 plus Cl2, and I'm going to cancel out these electrons, as I should when I have everything else balanced. And then my products will be 2 Fe3 plus my 2 Cl negative. So this is the first step if you were asked to find the cell potential, first you would have to do this based on the cell diagram. This question does not ask us to go any further, so we will stop here, and that is our overall reaction that will occur in this full-take cell represented by that cell diagram.